So the simplest graph that we can possibly do here is something like r equals 4. That's a graph. We can graph that. What is that?
Fourth level.
Say again?
It's just the fourth level.
Radius? Oh, no.
Yeah. So is there anything specified for theta?
No.
So theta is arbitrary. It can be anything, right? But the radius, the distance from the origin, has to be 4. So 1, 2, 3, 4. It could be here. It could be there. It could be anything inside here, a distance of 4 from the origin. Anything out here, a distance of 4 from the origin. This is a circle. That's a circle with radius 4. Anytime you get just r equals something, it's a circle with that radius. That make sense? For any angle you pick, your distance from the origin is 4. Well, anytime you have equal distance from a central point, that's a circle, isn't it? Yeah. What if we have theta equals pi over 6?
Just a line.
It's just a line, very good. So that tells us to rotate pi over 6, that's like 30 degrees. And r is not specified, so r can be anything. It can be anything on that terminal ray for pi over 6. So, it can be out 1, it can be out 2, 3, it can be as far as you want. So it can be anything out there. And it can be negative, so it can be anything this way. So when we state something like theta equals an angle, it is a line. Rotate from the positive x-axis that much and make a line. That's it. Now what's kind of cool though is when you do r equals theta. Any guesses?
Like an oval or something?
As theta increases, r increases the same, right? If we put in pi over 6 for theta, r is pi over 6. Pi over 2, r is pi over 2. 2 pi, r is 2 pi. So as theta rotates, r grows, right? This will create a spiral. As theta increases, r increases. So as you rotate, you get further and further from the origin, which will make a spiral. So those are some real basic ones. Just trying to develop a feel for what's happening here. Okay. Got a little bit of a feel? When we have no clue, like the very first time you ever graphed a parabola, y equals x squared, you had no clue what it was going to look like. What'd you do?
Plotted.
Plotted a table, didn't you? Made a table and plotted points. That's what we're going to have to do in polar here, because unless you've studied this before, we don't have any clue with what we studied so far in here, what these are going to look like. Okay? So we're going to have to plot some points. And we're going to do one of those, and then we'll call it a day. Let's do r equals 1 plus sine theta. Now, sometimes in function form, they will write this as f of theta. That'll be your r. 1 plus sine theta. Sometimes you'll see it this way. Okay. And again, in Pearson, I've been saying rectangular coordinates because that's the official math terminology. They're also referred to as Cartesian coordinates, named after Rene Descartes. So if you see Cartesian in there, that's what they're talking about. All right? All right, so I don't know what this, well, I do know what it looks like, but let me pretend I don't know what it looks like. We're going to make a table. And actually not R, we're going to put numbers in for theta, and then we're going to get R over here. Theta is the independent variable. Theta is like, you know, in that context, it's like X. It's the number we put things into. R is like Y. It's the result when we put those things into theta. And I'm going to choose numbers that give us some clean results here. So I'm going to choose numbers like 0, pi over 6. I'm not going to choose pi over 4 because that'll give us a root. I'm not going to choose pi over 3, that'll give us a root. Pi over 2, 2 pi over 3, no, not 2 pi over 3, forget that one. 5 pi over 6, pi, 7 pi over 6. Let's jump to 3 pi over 2. And we're going to do 2 more. We're going to do 7 pi over 4. No. 11 pi over 6. And 2 pi. And then we'll plot them over there. All right, when we put 0 in for theta here, what's sine of 0? 0 plus 1 is 1. There we go. Put in pi over 6 for theta. What is sine of pi over 6?
Half, 1/2.
1/2 plus 1. Get a common denominator. 1 over 2 plus 2 over 2 is 3/2. Yes? Pi over 2. What's sine of pi over 2? 1. So 1 plus 1 is 2. So these are ordered pairs, R theta. R is 0, theta is 1. No, wrong. Theta is 0, R is, come on, it's 1, 0. They go in the order R theta, okay? It's backwards of what we did over here. Theta is the independent variable, it's backwards of X and Y. Does that make sense? Theta is the one that we choose values for, R is the result. So 1, 0, and 3/2 pi over 6, and 2 pi over 2. Next one, 1 plus sine of 5 pi over 6. What's sine of 5 pi over 6? 3/2 again. So 3/2, 5 pi over 6. What's sine of pi? 0. So we got 1 pi. Sine of 7 pi over 6? Negative a half. 1 minus a half is a half. Three pi over 2. Sine of 3 pi over 2? Negative 1. 1 plus negative 1 is 0. Okay, 11 pi over 6.
Negative a half.
Good job. Oops, 1 plus negative a half, which is 1/2. And the last one, 2 pi, sine of 2 pi. 0. Writing sideways here. So we got 1, 2 pi. All right, let's plot these. Let me calm down here a little bit. All right, this is r theta, so these are not xy coordinates. 1, 0 means we go out 1, rotate 0. There's a point right there. 3/2 pi over 6. There's 2, so 3/2 is halfway. Rotate pi over 6. It'll be on the circle that goes through there. Like that. 2 pi over 2. Out 2, up pi over 2. That's pi over 2, that's pi. It's 3 pi over 2. 2 pi, 0. So, 1, 2, at a point there. 3/2, 5 pi over 6. So 3/2, again, is halfway there, between 1 and 2. 5 pi over 6 is way over here. It's like 150 degrees. So far this graph is doing this. 1 pi, so it's coming back in here, that's there. 1/2, 7 pi over 6, so you go out a half, rotate 7 pi over 6. It's going to be in here. 0, 3 pi over 2, so rotate all the way around down there and you go out 0, it's at the origin. 1/2, 11 pi over 6. 11 pi over 6 is this way, it's like 330 degrees. And a half be around here. And then we're back 1, 2 pi. So all the way around is 2 pi and 1 is out there, so it took us back to there. There's the graph. Just like when we graph y equals x squared, we call it a parabola. In polar form, we call this a cardioid. Let's give Desmos another chance. Check this out on Desmos. Well, I already got it on there, actually. So here it is. We call that a cardioid. Let's see what happens if we put cosine in there for fun. Oh, got another cardioid going that way. That's the one we just did. I don't know what tangent will do. Tangent does weird stuff. So, we're going to learn, I don't know how far we're going to get to go, but we're going to learn how to manipulate these, just like you manipulate parabolas, make them open wider and all that stuff. Watch this, if I put a 5 in there, look at that. I get 5 petals of a flower, but if I put in 4, oh, 4 petals. But check this out, if I do cosine, it's different. If I do 5 theta, you got your 5 petals, but watch when I do 4. Get 8. Get twice as many. If I do 3, I need 6. The even numbers give us twice, I think, 6 is 12. So we're gonna play with this stuff, and then we need to apply calculus. We need to find the slope of a line tangent to this, the derivative, and we need to find the area inside these things. Yeah. We'll do that next week, hopefully. Have a great day.